Hello everyone, this is your tutor AB. Today we're going to be solving a problem from the May 2024 IB Physics HL examination. This is a paper 2 problem from the Times at 2 paper. Okay, this relates to the topic of thermal physics. Okay, let's get started. Crushed ice of mass 35 grams at temperature negative 10 degrees Celsius is placed in a warm room. The graph shows the variation of the temperature T of the ice with the time T. Now make this distinction. Big T represents temperature, small t represents time. Now this is something you don't want to get confused when doing the problem. Now this graph right here represents the scenario. Okay, they tell us that the specific heat capacity of the ice is 2100 joules per kilogram per Kelvin. So part A, show that the average rate at which thermal energy is being transferred into the ice is about 3 watts. We want to prove that the rate at which energy is being transferred into the ice is 3 watts. Okay. So look at your formula booklets and think to yourself, what formula has the term for the specific heat capacity? Now there's only one formula, and that is E is equal to mc delta T, where E represents energy. Okay, and C is of course your specific heat capacity. Okay, now they don't want us to solve for E, they want to solve for the rate at which thermal energy is transferred. They want to solve for the change in E. Okay, and what is the change in E? If you look at your formula booklets, right, for the new syllabus, this would be in your topic A section, you would find that the change in energy is nothing but power. Power is nothing but E over T, delta T in this case. Power is nothing but E over T. Power is the rate at which energy changes, and that's what they want us to find. They want us to find the rate at which thermal energy is being transferred. So the rate at which thermal energy of the ice is changing. So we have the term E, but we wanted to write it in terms of P, power, because that's what we want to solve for. Because 3 watts is a unit of power. So we can rewrite E as P delta T is equal to MC delta big T. Right? Now let me just move this somewhere else, for example right there. And okay, so we need to solve for power. So power is nothing but MC delta T over small t. So what is power exactly? It's the mass times the specific heat capacity times by the change in temperature all over the change in time. So let's find out. Let's put this in our calculator. We get the mass is 35 grams, which we need to convert to kilograms. So that's 0.035 times by the specific heat capacity, which is 2100, times by the change in temperature. So what's the change in temperature? We can see that energy is being transferred from here to here. There is a rate, so from negative 10 to 0. So we can just say that delta T is 10. So it's 0.035 times by 2100 times by delta T, which is just 10. And it doesn't matter if it's Kelvin or Celsius, because the change is same for both units. And the delta T, this change in time in which this thermal energy transfer occurs, and that's from 0 to 4 minutes. So that's 4 minutes. So that's in seconds, 240 seconds. So if you put this all in your calculator, what do you get? You get 3.06 watts, which is approximately what they wanted us to find earlier. So we've proven their statement. Okay, estimate the specific latent heat of fusion of ice. Now, what exactly is specific latent heat of fusion? Well, it basically tells us how much energy per kilogram do you need to change the state of a substance from one to another. So for in this case, how much energy do I need to change the state of ice from ice to liquid, which is water? So what formula in your data booklet includes the specific latent heat of fusion? Well, that is nothing but E is equal to ml. And now what did we say E was equal to? E is nothing but power into delta T, right? Power into delta T. And that's equal to ml. Now we calculated power earlier. It's a constant power throughout the whole process. That's 3.06 watts. So you can write here 3.06 watts times by the delta T, which is the change in time in which this power is acting on the ice to change its state. Okay, now how do I know on this graph how long the change of state is occurring? Well, a change of state occurs when the internal energy increases but the kinetic energy stays the same. So in this case, internal energy is increasing because there's a constant addition of energy into the ice, but the change in temperature is the same. And that's because during a phase change, kinetic energy does not change. So how do I know at what point of this graph there's a phase change? From 4 minutes to 64 minutes, there's a phase change. Why? Because there's no change in temperature, but a constant energy is being supplied into the ice to change its state. So for a total of 60 minutes, there is a phase change occurring. So that's 60 minutes into seconds is 3,600 seconds over the mass of the ice in kilogram, which is nothing but 0.035. This will give us the specific latent heat of fusion. So putting this into our calculator, 3.06 times by 3600 all over 0.035, and that gives us this exactly 314,742 2 joules per kilogram. You need this many joules of energy per kilogram to change the state of the ice from solid to liquid, which is water. Okay, now next question. Between 4 minutes and 64 minutes, solid ice and liquid water coexist at 0 degrees Celsius. Compare and contrast during this time the internal energy of the solid ice to that of an equal mass of liquid water. Okay, so what did I tell you? From 4 minutes to 64 minutes, a phase change is occurring. That's why there is some solid ice and some water coexisting at this point, because it's not yet a complete change in state. So what do I know? During this time, there is no change in kinetic energy, because we know the kinetic energy stays the same because there's no change in temperature from 4 minutes to 64 minutes. So the kinetic energy of both water and ice is the same. And we know this because temperature is directly proportional to kinetic energy. But there will be a change in internal energy, because what is internal energy? Internal energy is nothing but your kinetic energy plus potential energy. So although your kinetic energy stays the same, that's not the case with potential energy. Now you see, we're transferring energy into the ice to change its state. Because kinetic energy is staying the same, some form of internal energy has to be gaining this energy that's being added. And all because kinetic energy stays the same, potential energy is what's receiving this energy, additional energy, and is increasing. And therefore, because I'm adding energy into the ice, this energy being added into the ice is increasing the potential energy of water, and therefore the internal energy of water is greater than that of the ice, and this is simply because the potential energy of water is greater than the potential energy of ice. Why? Because we're adding energy into the ice to change its state. Because kinetic energy stays the same, this energy is increasing the potential energy, and therefore water has greater potential energy than ice. Okay, thank you for watching. Please like and subscribe. If you have any questions, leave it down below and I'll answer it as soon as possible. And also one more thing, I'll try to be more consistent with my upload schedule from here on out. Okay, thank you for watching. See you in the next one.